last class we discussed about the constructional details of three-phase induction motor and what are the different types of three-phase induction motors and their applications. In this class I am going to explain about the working principle of three-phase induction motor. The three-phase induction motor works on the principle of Faraday's law of electromagnetic induction principle, that is mutual induction. In third unit we discussed about the transformers. The transformers is also works on the same principle, that is Faraday's law of electromagnetic induction principle. Sometimes the induction motor is also known as the rotating transformer. Why we call induction motor as a rotating transformer? Because the stator or stationary part of an induction motor is connected to primary side of transformer and the rotor or rotating part of an induction motor is connected to secondary side of the transformer. That's why we call induction motor as a rotating transformer. But transformer is a static device, it doesn't rotate. Your induction motor is rotating machine. In three-phase induction motors, the three-phase stator windings is connected in star or delta form. The three-phase windings are displaced by each other by 120 degrees. When we can apply the three-phase supply to your stator windings, it exhibits rotating magnetic field which rotates at the synchronous speed. That means when we are giving the three-phase supply to your stator windings, if you can apply the voltage to your stator windings, the windings will produce an rotating magnetic field which will rotate at the speed of synchronous speed. According to the Faraday's law, an EMF induced in a circuit is due to the rate of change of magnetic flux linkage through the circuit. As the rotor winding in an induction motors are either closed through an external resistance or directly shorted by end rings. We have already discussed in construction. If in squirrel cage induction motors, the rotor bars are short circuited by an end rings, that is the closed path. In slip ring type of induction motors, the rotors are closed by some external resistances and cuts the stator winding magnetic field and EMF induced in the rotor copper bar, and due to this EMF a current flows through the rotor conductor. That is, when three-phase supply is given to your three-phase stator winding, the stator windings produces some rotating magnetic field. Due to that rotating magnetic field, according to Faraday's law, if field is produced, the magnetic field is produced, the rotor windings cuts the magnetic field and it produces some EMF. Due to that EMF, currents will be flow through the rotor conductors. Here, the relative speed between the rotating flux and static rotor conductors is the cause of current generation. Hence, as per Lenz's law, the rotor will rotate in the same direction to reduce the cause, that is the relative velocity. From this figure, the motor will be rotated. How the motor will rotate? When three-phase supply is given to your stator windings, the stator windings produces some rotating magnetic field in the circuit. Due to the rotating magnetic field, the rotor windings, that is the rotor is short circuited by some end rings or by adding some external resistance. The rotors, according to Faraday's law, the rotor cuts the rotating magnetic field, then an EMF will be induced in the rotor circuit. Due to that EMF, some current will be produced and in the conductor. Thus, from the working principle of three-phase induction motor, it may be observed that the rotor should not reach the synchronous speed produced by the stator. Why? Because due to the stator windings produced the rotating magnetic field, Due to that rotating magnetic field, your rotor will start. That's why the rotor speed never reaches the rotating magnetic speed, that is synchronous speed ns. If the speed becomes equal, there would be no such relative speed, so no EMF induced in the rotor and no current would be flowing, and therefore no torque will be generated. Then your motor will always in rest position. So the RMF, rotating magnetic field, the RMF is nothing but the magnetic field which is present in between stator and rotor of an induction motor is called as rotating magnetic field. Here the speed, the rotor RMF speed is denoted as synchronous speed, that is ns. It can be denoted as ns. Ns is here synchronous speed. Ns is equal to 120 f by p, where f is the supply frequency in hertz, p is the number of poles. Next, slip of an induction motor. The induction motor, the slip is defined as the difference between the synchronous speed to the rotor speed with respect to the synchronous speed. If you want to find the percentage slip, we can multiply with 100. Here from this relation here, S is equal to slip, Ns is equal to synchronous speed, N is the rotor speed or actual speed of the rotor. If you want to find the slip speed, that is difference between synchronous speed to rotor speed N. When stator is stationary, that is motor in rest position, that is your induction motor doesn't run at the time of starting, then the speed of the induction motor, the rotor speed is 0. That means we are not giving any supply to your stator winding, so your motor is in rest position. In this condition, your rotor speed n becomes 0. Substitute this n value in the slip value, that means ns minus n by ns. From that equation, at the time of motor or standstill condition, slip becomes 1. How it becomes 1? At the time of motor rest position, n becomes 0, then the slip becomes 1. If you want to find the percentage slip, multiply with 100, that means we get the 100%. At the time of starting, the percentage slip of the induction motor is 100%. When n is at synchronous speed, when nr is at synchronous speed, the slip becomes 0. That means if ns equal to nr, that is stator speed equal to rotor speed, then the slip becomes 0. So the motor never runs at synchronous speed. The slip in the three-phase induction motor from no load to full load is about 0.1% to 3%. That's why the induction motors are also called as constant speed motors. Thank you.